Today I will to discuss a central challenge in natural language processing, aligning large language models with humans' intent, ensuring they are helpful, honest, and harmless. To achieve this, reinforcement learning for human feedback, which means RLHF quickly established itself as the mainstream paradigm. Within the RLHF framework, Proximal Policy Optimization (PPO) serves as the industry standard. PPO relies on an online exploration mechanism by introducing a clear surrogate objective. It strictly confines policy updates with a trust region to balance chaining efficiency and stability. Because PPO actively explores environments and generates entirely new reasoning trajectories, it dominates complex reasoning tasks, such as mathematical derivations and code generations. However, PPO's actor-critic architectures demands maintenance for massive neural networks in memory simultaneously. It is computationally exhausting, highly sensitive to hyperparameters, and prompts to reverse hacking, which models exploits systemic blind spots to generate high-scoring gibberish. To address these engineering nightmares, researchers proposed a lightweight alternative: direct preference optimization, which means DPO. DPO achieves an ingenious mathematical equivalence transformation that completely bypasses the time-consuming rewards model training phase. It reduced the complex reinforcement learning program into a simple supervised learning paradigm based on a binary cross entropy loss function. This sampling freeze and dual model parallels architecture cuts memory requirements by over 50% and reduces training time to just a fraction of PPOs. DPO has revolutionized the open source ecosystem, excelling in general dialogue task and format alignment. However, DPO's extreme architectural simplification comes at a cost because it relies purely on offline learning from preference datasets. It lacks an active exploration mechanism. When faced with out-of-distribution complex reasoning tasks, DPO models often fall into hallucinations. Furthermore, DPOs utilize a sequence level loss function. If a model makes a single error at the end of a long reasoning chain, DPO indiscriminately pe- penalizes the entire sequence, severely undermining the fine-grained credit assignment requires for multi-step logic. In contrast, PPO can leverage fine-grained process reward models to pinpoint exact errors while preserving correct, correct intermediate steps. In conclusion, there is no signal absolutely perfect method for alignment. PPO is an online explorer that chains systems complexity for high performance selling, while DPO is an offline learner that chases reasoning limits for extreme efficiency. The future trend points towards a hybrid alignment pipeline. Emerging industrial practice often use DPO first to establish fundamental safety guardrails, followed by high-cost PPO training to push the limits of complex logical reasoning. Ultimately, future alignment paradigms will dynamically balance computational constraints with specific task requirements. That's all. Thank you.